In the teaching model number 4, we will explore the representation and the interpretation of fragmentation patterns for alkanes and a few other functional groups. I want to highlight again that our intention is not to interpret every particular peak in a mass spectrum, but there will be certain patterns that will be helpful in actually distinguishing one molecule from another. So we start off with the simple molecule of pentane, and you can see that right here I have a structural representation of the molecular ion. It is a radical cation in that we have the cation and also the single electron. When the parent molecule had an electron knocked out, we don't know exactly where that happened. And it's not actually that important to know this. And so there's just this uniformal representation that somewhere in that structure there is a bond between two atoms that involves just one electron. When we start to look at the fragmentation, we then in a sense differentiate. So for example, in that first fragmentation where a methyl group is lost, presumably from the terminal part here, we're saying that this bond gets severed. So it must have been that bond that had a single electron. As a result, there will now be a cation on this terminal carbon, and we will lose this particular radical. One of the patterns that you're going to notice is that there will always be the cation that gets detected, and there will always be the radical that is the thing that gets lost. This is the typical pattern in these sorts of fragmentations. The other thing to notice is that there'll be very common sorts of fragments that get lost, like an M-15, an M-29, and M-43. M-15 corresponds to a loss of a methyl radical, -29 an ethyl radical, -43 a propyl radical. Those are common moieties in an organic structure. You'll see in the mass spectrum that often we don't even bother to indicate what the actual M/Z value is, but rather we're indicating what got lost. Furthermore, I'll mention that often in a mass spectrum, these sorts of M- values aren't actually given, but rather you'll need to calculate them. And so being able to calculate them will help you figure out, well, what fragment does this correspond to? I will also point out that, as you can see, this here is the base peak. It's not actually clear why that is going to be the base peak. Why is that the most abundant fragment? If we look at all these fragment patterns, they all result essentially in a carbocation that, as we will discover a little bit later, is a primary carbocation that's not particularly stable. So it's not clear why the M-29 is the one that is the base peak, nor would we ever ask you to explain that particular pattern. But if we go on to the next fragmentation involving 2,2-dimethyl pentane, you'll see that sometimes we can actually speculate why certain peaks are the base peak. In this particular mass spectrum, you can see that the molecular ion is represented right here. If we hadn't shown you that this is where it is, you would not have known. Clearly, the molecular ion is not very stable, and it was completely fragmented. Now, in this particular case, you can see that the base peak corresponds to an M-43. When we look at the structure of the molecular ion and we speculate, well, what gave rise to that base peak, I hope it's clear to you that essentially this bond was severed. So in other words, there would have been a single electron between those two carbons. The electron went with this particular radical. Now that would be the loss of a 43. And we can see that this would be a 43 by doing a very simple calculation. So this would be the C3H7. And so the nominal mass for this would be 3 times 12, which would be 36, plus the 7. And so that equals the 43 atomic mass units. And so, of course, that corresponds to the M-43 peak. Now, why is that the base peak? Well, notice that the carbocation that's generated here is a carbocation that's surrounded by 3 other carbons. Now, we'll be discussing this quite a bit more later in the course, but right now let's review a little bit. So this is under the idea of stability of carbocation. So in general, carbocations are not stable. They're not stable because the carbon, one, has a formal charge, and secondly, lacks an octet. We can classify, though, different kinds of carbocations as a methyl carbocation, a primary carbocation, a secondary, and a tertiary. The methyl carbocation is the one that looks like this, where essentially we have a methyl group and then a positive charge associated with the carbon. A primary carbocation would be something like this. So you've got a CH3, CH2, and it's the CH2 carbon that has the positive charge. A secondary carbocation would be a carbon, let's say, bonded to a CH3, and then bonded to another CH3. Of course, there'd be a hydrogen here, and the positive charge again is on the central carbon. And lastly, a tertiary carbocation looks like this, with the positive charge on that central carbon. Now, in terms of stability, the methyl, of course, would have the lowest stability, and the tertiary would have the highest stability. The reason for this has to do with the fact that electron density can be pulled from the carbons and somewhat stabilize this positive charge. It's being pulled by induction and also by something that we call hyperconjugation. As mentioned, we'll be discussing all of this later. But for now, I'd like you to remember that a tertiary carbocation has some relative stability. And therefore, in terms of the various kinds of fragmentation, it's not surprising that this M-43 cation is the one that occurs the most and comes up as the base peak. Let's consider this question then. Gives us a little bit of practice considering how fragmentation might happen with an alkane. I'll ask you to read the question, perhaps attempt it, so you may want to stop the video, and then I'll go over the answer. So one, we'll need to actually draw out the structure. So we have a 1, 2, 3, 4, 5, 6 carbon chain, a hexane. There are 2 methyl groups on carbon number 2. We know that the mass of this is 114 atomic mass units, and we know that there's a base peak happening at M-57. So we're asked to draw the fragmentation responsible for the formation of M-57. So we're actually showing a process here. So this is the typical format. I'm going to start with my molecular ion, radical cation. So I put brackets around this whole thing, positive dot. And then I'm going to show what gives rise to this M-57. Similar to the previous example, you might expect that actually the bond gets severed, for instance, right here. We can check that the fragment that gets lost, which will be a radical, is this 4-carbon radical, and I'll put the single electron on the end here. So we can calculate the mass based on the molecular formula. The molecular formula will be C4, and not H10 in this case, but rather H9. And so therefore it'll be 4 times 12, which will be 48, plus 9 atomic mass units, which will equal 57 atomic mass units. So it makes sense that that would be the fragment that's lost. The fragment that remains will be the carbocation, and I know that the positive charge would be right here, and I also know that this is a tertiary carbocation. So it would make sense that that would correspond to the base peak. So that would be the fragmentation pattern, and it would explain or justify why we have an M-57 base peak. You are asked then, well, why is it that the M-15 plus is not the base peak? So let's explore. Once again, I'm going to draw the molecular ion, a radical cation. Now, if we just lose a 15, perhaps we would have this bond that's cut, which is quite possible. Let's see what remains. So there'd be a carbocation right here. Here's the rest of the chain. And of course, we would end up with this methyl radical. and that would correspond to the 15 that's lost. So why is situation A better than situation B? Well, you can see that in terms of the cation, both result in a tertiary carbocation. But in terms of the radical, here we have a primary radical, and down here we have simply a methyl radical. So what I said about carbocations and their relative stability also applies to radicals. So as you might imagine, a primary radical is a bit more stable than a methyl radical. And therefore, it is indeed going to be the M-57 that is our base peak.